There you go. So, human evolution. We can see we start from very basic self-replicating molecules about 4.3 billion years ago. 4.3 billion years ago. Remember, the Earth is only about 4.5 billion years old, right? So life started very, very quickly, relatively speaking. Right after the Earth got cold enough to do so, life began. And from protocells, remember, these are basic things. Lipid bilayers, lipid molecules, right? Very basic molecules. Things like RNA. And from here, we have prokaryotes, right? Basic, simple, self-replicating cells that single-celled organisms, much like bacteria. But even more simpler than bacteria. Bacteria come along about 3.5 billion years ago, and they become able to, photosynthesize, things like that. The first photosynthesis takes place about 3.5 billion years ago. The first oxygen is produced. Because remember, the first billion years of the Earth's history, there was no oxygen in the atmosphere. So, and then we have eukaryotes, even more complex single-cell organisms. That's what eukaryotes are. This is what developed the nucleus, mitochondria, right? Cytoskeleton, a more elaborate structure, right? That's a eukaryote. So it took 2 billion years for these simple-celled organisms to become more complex. And then we had the first animals about 800 million years ago, maybe 800, 900 million years ago. The first mouse right here, right? This is an organism with a mouth, with muscles, with nerves, with eyes, right? This is the first organism that we come from. That was an animal, part of the animal kingdom. And from there, they became different. They developed different tubes. A heart emerged, right? They looked like worms, right? The first worm-like structures, animals. And then we have Deuteriosum about 600 million years ago. Remember, these are all in the ocean. They all lived in the oceans. And then the first gills evolve in these animals. The first allows them to breathe underwater and get more oxygen. They're able to fuel their bodies even more. And then it comes to Pachyas here. Resemble more like fish, right? With more longer tails, brains, the first brains, neural networks, blood vessels, right? Nerves, starting to become really an animal, a very complex organism. And then we have about 400 million years ago, the first teeth, the first stomachs, spleens, lungs, right? Now we're more like fish, right? Now we're back. Now we're the first fish here, and these fish now developed protolimbs, which their fins were able to become arm-like structures, and then Tiktaalik, 375 million years ago, was what we think is the first animal on land. And it didn't walk on land, right? It took, again, many generations for this process to happen, for those protolimbs to eventually become longer limbs, enabling them to walk more on the land. Then we had the first amphibians, about 350 million years ago. The first reptiles, more complex eye structures, stronger bones, a more complete rib cage. The first legs. So they were walking faster, they were running, walking, crawling faster. Able to eat things more, carnivorous animals. They were able to eat other things on land, other amphibians. So they had tongues, they developed teeth, and more developed hearts, bladders, digestive systems, things like that. And then from here we had the first reptiles 300 million years ago. And then warm-blooded animals, right? Some of these reptiles became more warm-blooded, more advanced lungs, more advanced lymphatic systems, more different hind limbs that had arches in them so they can run faster, right? These are the first mammals. Milk glands eventually develop, hairy skin, specialized teeth, constant body temperatures, things like that. Then they had eggless births, right? More like mammals, like squirrel-like animals, marsupials, and then monkeys, monkey-like animals, forward-facing eyes, grasping fingers, things like that. And then the first apes, about 20 million years ago. That's where we come from, the first apes. They develop, larger brains, specialized vision, things like that. About 9 million years ago, they walked on fours. They started to lose their tails. They started to walk more upright, slowly but surely. Australopithecus afarensis, 4 million years ago, they're completely bipedal. Right now, they're walking totally on their 2 feet. And the first fires, the first clothing, wheels, about a couple million years ago, and then from there on, we became Neanderthals, the different other species of humans, and then eventually us today, right? So this process took 4 billion years of changes, right? Think of all these changes. And this graphic is very good because it's very short. But the point is that all these changes didn't just happen like Pokemon, right? This took billions of years of changes. Different genes developing, different animals, natural selection, right? Different environments that these animals had to go through, different, social environments, ways they work together, right? All these things had to happen for us to be the way we are today. It wasn't just one factor. It was a billion different things over many billions of years. So that's how we got here. That's how we evolved. And so now that you know that is what happens, the mechanism of evolution is through natural selection. So we can see here, look at this tree, right? Think of evolution like a tree. The first living things about 4 billion years ago, and from there they branched out, became bacteria, eukaryotes, more complex organisms, plants. We split off from the plants about 2 billion years ago, became protozoans, insects, fish, amphibians, reptiles, birds, and then mammals. And then here we are today as humans. You can't see it? There you go. Yeah, so you have to remember, you have to think of evolution like a tree. That's how it works. And it's constantly branching out. Always branching out. It never stops. The process never stops. Evolution's always happening. Never going to stop as long as we're living. So think of it like one thread, right? The way we got here was all the way over here, right? We took one path. But if you trace that one path back, you see that we share common ancestry with everything else here, right? Everything here shares ancestry with this, the first living organism about 4 billion years ago. So we are still evolving? Yep, we're still evolving. We're always evolving. Evolution's always going to happen. Does that mean we won't stay human forever? Yep. Well, there will be something after us. There will always be something after us. We're always evolving. Yeah, we're always evolving. Evolution doesn't stop at any point in time. So here's a better picture for you guys to see. Right. Think of it like a tree that's always branching out. But they all share a common stump, right? All these species share a common stump, a common ancestor. Nope, it's not a theory. Evolution's a fact. We can observe evolution in the fossil record, DNA, and here's how we know. So when we take a look at the fossil record, right, what we see is, for example, human arm, this is a cat arm, this is a whale arm, this is a bat arm. They all share similar fossils. In fact, They all share exactly the same arms. These are all the same arms. All the fossils here are color-coded. They're the same. We have the same arm structure as a whale. We have the same arm structure as a bat and a cat. We're no different than a whale. We're not different at all. There's no difference except for clearly, the lengths of the fingers. But whales have fingers. Whales have fingers. So do bats. So do cats. So do humans. Right? The humerus bone, the radius bone, all these bones are the same. Right? So that's how we know that we come from a common ancestor, because we can take a look at these fossils and we can look at the geological strata. Right? When we take a look at the geological timescale, when we dig up fossils, we know that there are different distinct layers under the earth, right? Under the earth, there are distinct layers of certain deposits of material. That's how we know the time in which these things happened. So, because the Earth's crust is always changing and moving. The Earth's crust is always moving. Deposits, rocks, dust, sand is always moving upon the crust of the surface, and this is what causes these layers to form. So the further down we go, the older those rocks are going to be. So when we find specific fossils in these geological strata, we can date the fossils. We know how old they are because we know how old the rocks are. We know how old the rocks are. The ground's not always solid. Of course it's not always solid, but the point is that over time, right, it becomes a geological strata. Of course there's water, there's rivers and all kinds of different, liquidy things happening on the surface. But over time, water eventually settles into aquifers or, evaporates. The point is that we have distinct layers in the geologic strata that we can date. That's how we know that when we find these fossils in the geological strata, we know that if we find them close together, we know that they share the most likely common ancestry. That's exactly how we determine that evolution happens. This is direct proof of evolution right here in front of your eyes. And interestingly, what we find is when it comes to whales, right? The reason why whales are mammals is because whales happen to be four-legged animals in their past. Look at this. Look how remarkable this is. That's a whale ancestor. We have the fossil. We have these fossils. This is called Pakicetus. And this was one of the whale's ancestors about 50, 60 million years ago. But what happened was over time, whales, they went into the waters, right? They developed webbed feet. Their hind legs became more webbed as well. Their tails became different. Their snouts became longer, allowed them to reach the air better, right? Because over time they went deeper and deeper into the waters. Again, the same process kept happening. Their tails became different. They resembled more like fins, and then their arms became smaller. Their legs became smaller, right? And now here we are today with whales of today, where they have full fins and very, very small hind legs. Whales of today, we actually know that they still have hind legs bones. They're vestigial structures. They still exist, but they're just not really functioning the way they did before. This is also evidence of common ancestry. When we find all these fossils, we found every single one of these fossils in the geological strata. So the point is that over time, a four-legged animal can become a fish-like species. Not a fish. Again, whales are not fish, but the point is they can become aquatic given enough natural selection, given enough changes, small changes over many generations. Remember, this happened over millions of years. Millions of small changes makes big changes over time. And that's how evolution works. And it's remarkable what you get, right? What we see in the fossil record is all these ancestors. All these ancestors here, we see them in the fossil record. And we can also see them in our DNA, right? So when we look at our DNA, we can see evidence of things like mutations, right? We can take a look at our DNA. We can sequence it. We can take a look at the structure of our DNA just like we can take a look at the structure of fossils. Hold on. I don't know why this is happening, guys. Okay, there we go. So, when we take a look at our DNA, come on. When we take a look at our DNA, we can see the structures of it, right? We can take a look at nucleotides. These are sugar phosphate backbones. These are the structures of that make up the staircase, right? We can take a look at the bonds between the different molecules that make up our genes, right? They're called base pairs. And this is how we look at our DNA. We can tell the different configuration of these molecules points to the specific genes that we have. So, and your DNA leaves a mark. It leaves a record of all of your DNA leaves a mark of all the different genes you had in the past. We can see the mutations. We can see all the different types of things happening to the genes. Right? We can see the DNA splitting. We can see all this stuff happening in our DNA, and we know that it changes. And it's hard to do mathematically, but we can do it. We can take a look at anybody's DNA and see the changes that happen inside of us. And that also proves that we evolved. Because if you know how something changes genetically, it corresponds to their fossils, well, now we have a more complete picture of evolution. So that's how we evolved. Any questions so far? We're going to talk about the Earth's formation next. Do we all have DNA, or just the government want us to believe it? No, we all have DNA. The government doesn't have a say in your DNA. You have your DNA is yours. It's who you are. It makes up who you are. What comes after humans? It depends how we evolve. Depends on the environments we see. Fossils don't prove a flood. There is no proof of a flood anywhere. There can't be a flood. So, now you know that how life happened. Now let's take a look at things like space, right? When we take a look at space, we know how, for example, everything has some DNA, but that doesn't mean we're fish. Yeah, where our ancestors were fish. Our ancestors were fish. Just like I showed you before, our ancestors were fish. We have fish DNA in us. We are, in a sense, fish. So, here's how the first planets formed. You have a big... No, I didn't lose it. No, the evidence that we're fish is in the fossil record, in our DNA. We have fish genes. Your ears, your jawbones, they come from fish genes. Anyway, so you have how the Earth forms is this way. You have a big ball of gas, a big sorry guys. Okay, you have a nebula, right? A large volume of gas in space, and what gravity wants to do is it wants to collapse, right? Gravity loves to make things collapse, right? That's what gravity does. It's a force. Well, you can consider it a force that attracts things together. So because of this, these gas clouds want to collapse, and they form disks. Because of angular momentum, right, these clouds want to form disks. And what happens is when they form disks, they spin. They start spinning. And the faster they spin, all that heat builds up in the center and becomes a star. The beginnings of a star. Now, how does a star ignite? Well, it has to burn off its hydrogen and helium. It fuses them together. It's something called stellar fusion. These elements make stars come alive. It makes them come alive. So you can see over time, all that gas and dust around the star, right, becomes eventually, because of gravity, planets, right? The planets collide together, they become larger planets, and you get a solar system. This is how our solar system got here. It's just physics, right? It's just gravity and physics. Here's a better picture of it. This is what gas clouds look like before, right? Before their star systems, they're very disorderly, they're very crazy, chaotic, but over time and gravity, they come together, become more orderly. They start spinning, right? The heat builds in the center, and rocks start to condense. Rocks start to precipitate from that gas, right? That gas precipitates. As it gets colder on the outside, the gas around becomes ice and rocks, little fragments. And they start to come together and they form planets, right? Look at all that dust there, right? Look at all the dust in the outskirts of this planetary disk, right? You can see as they spin and as gravity wants to collide them together, they become larger rocks. So think of planets like smaller rocks becoming larger rocks, like this, right? Imagine this being the case. And in space, because there's no atmosphere, there's no air really between these rocks, they easily connect together, much more easily than on Earth. In space, rocks love to collect together, especially metals. Very, very easily attracted to each other, especially with all the gravity. So that's what we think produced the solar system we know today. That's how we got here, right? Now, the Earth was, like I said, a big giant rock, but it was also really hot. The early Earth was a giant ball molten rock, almost liquidy. It was so hot that even iron, iron as we know today in weights, right? You ever go weightlifting? That stuff is typically solid. But in the early Earth's history, it was liquid. It was molten. It was liquidy. And because of this, very good animation there. Because of this, the Earth was a molten rock. That was very, very liquidy. And because of this, the heavier elements sank down due to density differences. They sank to the center, became the core, the lighter material. Because it was lighter, it was able to stay up top and rise up to the top and become the crust in the outer mantle. So the Earth and the Moon also, the Moon also formed in this way. The Moon was also another planet that smashed into the Earth, and that debris went out into space and collected into the Moon. Here's a very good animation of it. So let me show you how the Moon formed. This is a very good simulation right here. So here's Earth and here's another planet. See them smashed together, right? And because they were so molten, the liquidy, this was able to fling out part of the Earth flung out into space because of the collision. And it became part of the Moon. It became the Moon, right? This is what was left of the Moon, right? And it became this. Let me see. One of you guys want to see that again? So here, this is Theia. This is a Mars-sized planet, and here's Earth, right? smashed together about 4 billion years ago. A lot of that debris went out into space. It was so easy. It was such a great impact that a lot of that energy and matter went out into space. It started to orbit around the Earth because of the Earth's gravity. A lot of it went back in, but some of it stayed and became the moon. Some of it stayed in the Earth's orbit. And because of the position of it was in the Earth's orbit, it was able to stay there in a stable way. And it became the moon. That's quite amazing. That is quite amazing. That's how the moon formed. So, yeah, that's incredible. Now back to the Earth. The Earth was very hot as well. It didn't even have an atmosphere really that much. I mean, it was really gassy. It was hydrogen, carbon dioxide. But there was no oxygen in the early Earth's history, and it was still being bombarded by lots of rocks, being bombarded by it. But over time, as the Earth cooled down, it was able to become more suited for oceans. So how the Earth got its water is by asteroids. The asteroids impacted the Earth, and on the asteroids were ice and water. And this ice and water collected on the Earth and went into the atmosphere. It turned into water vapor. And eventually, over time, as the Earth cooled down, it was able to precipitate and rain down on the Earth and become the oceans, rivers, lakes, and things like that, and ponds. And that's how the early Earth was. Now, although the crust was able to cool down, the mantle and the core of the Earth are still hot today. They're still hot today, right? They're still liquidy iron today, because that's how hot they are. Because all that pressure pushing down on the Earth, like in the core of the Earth, right? Think of all that pressure, all that matter pushing down on the core of the Earth. That's actually, that pressure changes the way matter works. When something's under pressure, right? It changes the way that it changes the property of that matter. So even though, for example, on the very, very core of the Earth is solid iron because of the pressures. Even though it's super hot, because of the pressure, it's able to remain a solid. And that's why we have a solid core, but around it is the liquidy mantle. And because of this rotation between the solid core and the liquid mantle that revolves around it, moves around it, it's able to generate current, magnetic fields. And this is how the Earth's core works. But closer up to the surface, it's more colder. But again, that inner Earth is still molten. So what you have is volcanoes, right? What you have is that magma seeping up to the core because of it squeezes, right? It squeezes it up to the core. The continental plates shift. The crust can shift together, right? As it moves on this mantle, this liquidy mantle. It shifts together, right? It's constantly moving, and what you have is magma seeping up to the core, to the crust, and it becomes a volcano. That's what volcanoes are. Volcanoes is that magma from the mantle making its way up through the crust and onto the surface. That's how volcanoes work. So this convection, right? This mixing, this convection causes all that to happen. Now, you guys might be asking, well, if the surface of the Earth moves, does that mean that the continent shifted? Yeah, exactly. So here's the Earth today. Here's a very good graphic of continental drift here in plate tectonics. Right? Think of the crust as a sheet of rock that exists on top of the surface. And it's existing on this ocean of magma, right? So the crust can move on the surface, and that's what it does all the time. So let's go back in time. This is 10 million years ago, right? Look at this. Florida was underwater. If you're from Florida, you were underwater. I'm from Florida. My city was underwater about 10, 20 million years ago. Now you can see Africa and America were closer together. South America and Africa were almost touching. If you go far back enough, look at this. Look at that. Africa and South America are literally, they fit together like pieces in a puzzle. Look at that. They fit together. That's why. Right? Because at one point they were stuck together. And this is called supercontinent. This is a supercontinent. Right? This is about 200 million years ago. We had Pangea, where all the continents were shifted together. That's quite amazing, right? That's quite amazing. Now, because of this causes a lot of climatic shifts, right? The weather system of the Earth is very complex. At the equator, there's different pressures, there's different wind patterns than the poles. And this causes weather patterns to change over time, climate to change. So, in America, in the Northern Hemisphere, in the Northern Hemisphere, you had a lot of different climate than we had today. A lot of deserts, a lot of humidity in certain regions, a lot of swampy areas compared to today. This is what the Jurassic and the Triassic periods were like, right? A lot more heat. That's why there's no poles. Look at this. The Arctic had no ice on it. Look at this. There's no ice there. Just like Antarctica, the poles were green. They were green because the Earth's climate was vastly different than it is today, as well as because of the Earth's surface, as well as the currents. The currents were different than today too. And the currents also move a lot of that heat and distribute the heat around the world. So again, this is why the climate system is very complex around the world. And it depends on the ocean currents, what the atmosphere is doing, what the poles are doing, and all these things work together to become the climate system we know today. But yeah, this is 500 million years ago. Look at this. Another supercontinent. I forgot what this one is called. I believe it's called, I forgot what it's called. But yeah, look at this. Another supercontinent. So there were multiple times in Earth's history. Look at this. A lot of the Earth was almost all water, except for this area here, which was one supercontinent. So the geography of the Earth has changed drastically over the past 2 billion years, and it always will continue to change. In fact, we're splitting away from the other continents, and eventually in about a couple 100 million years, we will merge with other continents like Asia. But yeah, that's amazing to understand. What's up, Angry? The Earth is not flat. No, the Earth is a sphere. The Earth is demonstrably a sphere. We know it's a sphere. Yeah, it is awesome, right? So, and that's just a fraction of the history of the Earth. Now, let's take a look at, let's go back to the Earth's history again. So here we are, right? Now we have the Earth. You have convection, you have a magnetic field, right? Oxygen, the first oxygen is able to form. I'm sorry, we're a bit ahead of that. Okay. Oceans, right? The Earth has oceans now. It's still warm, still probably about maybe 120 degrees Fahrenheit all around the Earth. Still very hot, but it's cold enough to have liquid water on the surface. Water surface can survive, right? Ponds. And underneath the Earth, water can seep underground, under the crust. And we think a lot of this is speculation, right? But we think a lot of the early Earth life happened underneath the crust of the Earth. You have a lot of uranium, a lot of different radioactive elements under the crust that can be a heat source for catalyzing reactions to make the first life, right? These are very warm oceans, 100 degrees Celsius. Because of the pressures, they're able to be hot. So think of this environment, how conducive it is to things like, complex chemistry. We also have a very reductive atmosphere in the bottom and an oxidized at the top, and this allowed for the first life to form. On the surface, we have wet and dry cycles. We also have things like clay materials and phosphate materials that are able to mix with other molecules like ribose, like sugars and fatty acids. These are some of the first building blocks for life. These are some of the first building blocks of life. And look at what happens when they interact together, right? Fatty acids can come together and form a bilayer, like a filmy material, like a film. We call it a cell membrane. And what happens is, underwater, it forms a spherical structure and makes the first protocell. This is one of the first protocells that existed in the Earth's history. Then we also have amino acids, right? Amino acids come together and become peptides. These are longer chains of amino acids. These peptides can form longer chains of peptides into polypeptides. So these molecules, right? Think of all the complex molecules, and the convection of the crust, the mantle, the surface, right? Think of all the cycles that these molecules have gone through, the different reactions that they underwent. Well, we think that this is what caused the first RNA to form, right? The first RNA from basic materials, nucleotides, right? Chains of amino acids and peptides can become more complex things like nucleotides and RNA. And once this RNA gets into a cell, a protocell, well, now it has the ability to replicate, to begin the first replication processes. So that's how we think life started. Again, this is a very speculative matter, but this is what the best information we have tells us. The beginning of life was about 4.5 or 4.4 billion years ago, and that's how we got here. Now, remember, there was no oxygen in the early Earth's history. There was no oxygen. It took another 500 million years for the first oxygen to get to the Earth. But you don't want oxygen in the early Earth. That's bad for life. You don't want a very oxidative atmosphere for life. It destroys living molecules. What you want is a lack of oxygen, as well as things like UV radiation, because you want that oxygen in the atmosphere. It forms ozone, and this ozone layer can protect us from UV rays. But in the early Earth, it was not present there, right? So because of this, that UV radiation, much more higher energy intense radiation, was able to make its way to the surface and catalyze specific reactions to make living things. Where's my mods? Somebody mute these people. They're just babies. Okay. So again, that's how the first life got here, right? High energy environments. When you think of life, think of high energy environments, think of complex reactions. That's how life got here. That's how life began. Again, we don't have all the details, but the point is that these lipid molecules were able to form cells. Now, these cells are able to exchange different ions of sodium and different phosphates and begin to replicate. And once you have RNA form, you have the first DNA. DNA is just a form of RNA, just more complex. In fact, all you really need to make DNA is multiple RNA molecules working in synchronized together. So that's how DNA got there, right? DNA, again, the DNA of the past was not the DNA of today. Billions of years ago, DNA was not as complex as it is today, right? It was much more simpler. Today's DNA is the product of 4 billion years of changes, right? Think of those structures that are always linking together, right? Think of a very long chain. And think of DNA like a very long chain that's getting larger and larger, right? Different stuff is clinging onto it, becoming a longer molecule. That's DNA. DNA is a long strand of, proteins, things like that. Those are the instructions for who you are. That's what makes you who you are. So, But then once we had things like cyanobacteria emerge, you have the first oxygen, right, in the oceans. Life began in the oceans. And it started in the oceans, and then it came onto land about 600 million years ago. I'm sorry, about 400 million years ago. All right, so we have the first bacteria giving oxygen to the earth. And then we have plants. The first plants emerge about 2.5 billion years ago. The first tree, the first plant. Fish existed, the first plants, able to give work on photosynthesis. Continental drift occurred, like I was saying before. Sedimentary layers changed, right? Different. Here's algae, right? Now we have algae on the Earth's surface. The first land plants about 500 million years ago. And this changed the Earth's environment forever. Right? Now that we have plants on the surface, we have now a food source. We have habitats where fish from the oceans could potentially thrive in, right? So how do we get from fish to living on land? How does that happen? Well, you can see fish here, right? That was just a perfect, beautiful animation. You can see fish here. Look at their limbs, right? Look at their fins. You see how their fins, over time, transform slowly, but over generations, into arms. Fins are, in a very interesting sense, arms. Right? Like I was saying before, if you go back to the fish example, they have all the bones required to make arms. So our arms are, in a sense, products of fish fins. Of course, we've developed much more since then, but the point is that fish have everything you need for the building blocks to make a human. Now we have more complex trees on the surface. And now look at this. The first fish were able to make their way because they had long enough limbs, proto-limbs, again, not arms yet, not arms of today, but very primitive sense of an arm, was able to make it on its way to land. Right? And the reason why they went on land is because they had more food. There was more food there. There were new habitats. There was perhaps potential to escape from predators. Right? And these things allow these fish-like species this is called Tiktaalik, one of the first land animals we ever seen. They're able to now thrive at least partially on land. Now, of course, they were amphibious in a way. They lived mostly in the waters, but they were able to perhaps, lay eggs on land, right? Look at the habitats that enabled them to, thrive on land and go further and further into land eventually. Right? So that's how that happened. That's how we got onto land. It wasn't just one day. Again, it's hard to fathom billions of years. But again, what you've just seen was a process that took millions of years, millions of generations. Now, when it comes to the Earth, because of the oxygen, we were able to now have an ozone layer that protected us from cosmic rays. But unfortunately, it's not perfect. We don't have perfect protection. There were many instances where there was mass extinctions because of perhaps, volcanic eruptions or asteroid impacts or cosmic rays. Perhaps there was a supernova nearby or a cosmic event that spewed radiation to the surface of the Earth, and that changed the climate and it killed animals. The oceans also require oxygen for fish. A lot of fish today need oxygen. If that oxygen doesn't, if the oceans are not cold enough, a lot of fish can die. So these climatic events can change the biosphere of the planet. It can change the array of species we see. And that's why extinction on the planet of Earth extinctions are the most common things. Survival is very hard. Extinction is the norm, right? Extinction is what normally happens. It's very difficult to survive on the planet of Earth. But because of our ancestors, like these mammals, right, that survived the impacts, right, the fittest ones that survived, the fittest ones, right, the ones who can, survive better and adapt better, more quickly, they survived, right, and they became the mammals of today. Now here's dinosaurs, right, the first reptiles split off to become dinosaurs. And dinosaurs roamed the earth for, 200 million years. They were dominant. They went out to almost every continent of the earth, including Antarctica. Because remember back then, if you remember the picture from back then, Antarctica was very much warm. It was mild temperatures, 50, 60 degrees Fahrenheit, which is about 20 degrees Celsius. So dinosaurs could live anywhere on the Earth's surface because it was very, very warm, very good climate for them, very stable climate. But as you guys know, about 60 million years ago, something catastrophic happened. The asteroid impact. Right? A massive asteroid about 10 miles wide struck the Earth, and it destroyed a lot of the dinosaurs. 75% of them died. But again, some of them survived to become today's birds. So today's birds are dinosaurs. The birds of today are dinosaurs. Whatever you see, so when you look at a bird outside, that's a dinosaur. Birds are literally dinosaurs. They are the remnants of the dinosaurs, the ones who survived the impact. But after the impact, a lot of the mammals began to emerge because they were more fit to survive on land. And we have them become marsupials, squirrel-like animals, and then monkeys. Yes, all birds are dinosaurs. Yes, ostriches. Even the birds you see in your neighborhood. So monkeys eventually emerged about 40 million years ago. The first monkeys, the very, very primitive monkeys that we are ancestors, that we are descendants of. More continental drift, more changes in the environments. And the first humans, right? Now we're human. This is the first human the first species. There was no first person, but this is one of the first species of human that we think existed. And they developed fire. Nope, it didn't just pop up. Again, this took millions of generations. Again, let me reiterate this for you guys. Let's go back to this diagram. Again, this was about right here, this picture, about 65 million years ago. This is right after the impact. All right. These are tree-dwelling animals, right? Not monkeys. These are tree-dwelling mammals. But eventually, over time, they developed different sinuses, different menstrual cycles, things like that. They became more monkeys. And this is the first ape, right? The apes, Proconsul is a descendant of of monkeys. They lost their tails, right? Apes don't have tails, right? Because they didn't need the tails to survive in trees anymore. They survived more on grasslands, things like that. But as we went further and further out into grasslands, we migrated across Africa, right? Humans became bipedal. And again, we have all these fossils. You guys are, oh, this is crazy, but we have all these fossils we have. We can see the fossils, and we can see the DNA. We can see this in our DNA. We know that we share ancestry with chimpanzees. Right here, around this area, right? This is where we and chimpanzees split off, but we went this way and we became human, right? So again, this didn't take a day. This isn't like Pokemon, Again, of course, it took much more longer than you can even imagine. But the point is, over long periods of time and enough small changes, you have humans. Right? Now we developed fires, larger brains, we looked up at the night sky, and this allowed us to ponder our existence, right? Deeper thoughts, logical thoughts. And this changed us forever. This is what makes us human. Then from there we migrated through Africa. So here's Africa. We migrated into, the Middle East and Eurasia. This is Eurasia. And then Europe, about 50, 60,000 years ago. Eventually, so here's a great graphic. So here's Russia, right? Here's Russia, Siberia, Russia. And here's Alaska in America, right? So about 15,000 years ago, this was during an ice age where the Earth was cold enough that between Alaska and Russia, there was a land bridge. And this allowed, because it was so icy, right? Ice was able, the water was so thin here that ice was able to survive. Ice was able to become a land, basically connecting these two continents. So humans were able to walk across it into America. And we survived the cold climates, right? We had to survive the cold climates. We moved out into the United States, Mexico, and then South America, right? This is where the Mayans came in. This is where Mayans come in. There weren't humans yet? Yeah, there were humans 200,000 years ago. There were humans like us, Homo sapiens. We're a 200,000-year-old species, right? There were many people before us, many civilizations before us. But this is where we invented agriculture, right? The Mayans began the first astronomy, the first sciences, right? 5,000 years ago, more urban populations developed, more cities, the first larger civilizations, more different tools, 2,000 years ago, religion spread across Europe, in Asia, in Africa, and of course we have the Crusades, but a lot of scientific knowledge emerged from that era, right? A lot of scientific knowledge emerged from people who thought about the world. They were thinkers, but there were also lots of wars, right? Of course, we all know that. But over time, we have the Industrial Revolution. We developed steam engines, cars, planes, and this allowed us to connect together to one global civilization. Right now, we are one global civilization. Right? I can talk to somebody from another country right now. We are more connected today than ever before, and it's because of the way we did technology. Right? So now we have cities. But think of this. Think of our history. This is amazing. Quite amazing, our history. Exactly. Science allows us to have all these things we have today, right? Phones, TVs. If it wasn't for our ancestors who were thinking deep about these questions, trying to understand the world, we wouldn't have phones. We wouldn't have any of this stuff. That's how science is so important in our world. Any other questions so far? Did science originate from religious men? Well, most people were religious back then, but science did not stem from religion. Science stems from people who were thinkers. They just happen to be religious. But religion is not science. They're different. They don't mix together. Science is based on evidence and experimentation. Religion is based on story. The point is that the endeavor of thinking about where you come from and who we are, that is what ignited us to spark to this age of, the Renaissance and all these things that sparked intellect and technology and the Industrial Revolution. If it wasn't for those thinkers, we wouldn't be here. We wouldn't be here today. Great lesson. Thank you. What about the end of the universe? Well, I want to talk about stars. I want to talk about how stars work and how the elements that make you up got caught here. How did the Big Bang happen? Yeah, we'll go over that too. But yeah, to understand the Big Bang, you really have to understand stars in a way. Yeah, so think of our sun, right? Think of our sun here. It's a big ball of plasma, right? That's what the sun is, right? Well, the sun in the sky. Well, it's not in the sky, by the way. It's 93 million miles away. But the point is that sun that you see, it provides us all the energy that we have on our planet. It provides energy for you, and indirectly. Right? It feeds the plants. Plants use the energy to make sugars, right? You eat the sugars and you become a person, right? So the sun is our star. The sun is a star. It's a very big ball of plasma that generates energy, right? But how does it do this? Well, it's not fire. The sun isn't fire. There's no combustion going on here. What's happening is what happens when you have giant amounts of mass, you have a lot of pressure in the core of it, right? Think of all that mass, right? Think of how much stuff is in the star, a lot of plasma, gas. And that center of it is extremely, extremely hot. Extremely hot. But gravity wants to pull in the star, right? Gravity wants to pull in the sun. But you also have stuff inside the core happening. And what's happening is something called fusion, stellar fusion. And what this means is inside the cores of stars is so hot that atoms moving quickly can smash together. And what happens is they form a larger atom as well as expelling off some energy. But that's how it happens, right? In the core, atoms are moving so quickly, hydrogen, helium atoms, that they smash together, they fuse together and become a larger element, like helium, right? So two hydrogen atoms can fuse to become helium. And of course, they expel energy in the form of light, right? So when you see light, the light you see from the sun is being produced by those elements that are fusing together millions of miles away, making their way up into through the layers of the sun to the surface and going out into space, reaching your eye. And that's literally how the sun ignites. Because all that, now think of this happening on a much larger level, right? Think of all these atoms, right? Smashing together inside of the core. Well, what happens is that's all those atoms are expelling so much energy, right? Because there's a lot of stuff in there, right? So a lot of energy is being pushed out, a lot of light, a lot of heat, a lot of radiation is being pushed out so much that there's a pressure, an outwards pressure that builds up. Right? So think about it, right? There's the outwards pressure, but you also have inwards pressure, right? You have the gravity pressure putting pressure on the sun to be stable. So what happens is an equilibrium is reached. An equilibrium is reached in which the pressures are the same. And this is why our sun is stable for billions of years, because the pressures are able to remain this way because there's enough stuff in the center, in the core, for it to ignite. So the sun is burning enough energy to remain stable for billions of years. And again, our sun is about 5 billion years old. It'll last another 5 billion years. We're in the middle stages of the sun's history. The Earth is middle-aged guy. But eventually, now again, our sun has enough energy to fuse things up to carbon. So, again, if you take a look at the periodic table of elements, most elements are a bit larger than carbon, right? Carbon is number 6, right here. Most of the heavier elements are, much more massive than carbon, right? Carbon only has about 6 protons, but look at iron, has like 26 protons. Look at lead, has 82 protons, much more massive matter. So where does this come from? Where does all this matter come from? Where does all the heavier stuff come from? Well, the heavier stuff comes from larger stars. So inside the cores of even larger stars, right? Some stars could be 10, 20, even 100 times more massive than our sun, right? So think of how much more stuff is there. Think of how much more energy is in these massive stars. Think of how much more energy there is to expel. Well, what's going to happen is all that intense pressure, right? The sun's core is billions of degrees. Billions. We're talking billions of degrees. Billions of degrees. That amount of energy, that amount of pressure, right? Stuff happening on the small atomic level, that is going to cause a gigantic reaction, right? And that's called fusion. But when it comes to elements that are heavier than carbon, well, that's where they're produced, the larger stars, right? So here's the different layers of a star can fuse different elements. Typically, the elements of closer to the center are going to be more energetic. Hence, they're going to be larger elements being burned, right? Up to iron. So in the outer layers of the star, we have hydrogen fusion, right? Some larger stars, red giants, can fuse hydrogen. Then we have helium, which is a little bit bigger than hydrogen. Then carbon, which is a little bit bigger. Then oxygen. And then we have magnesium, neon, magnesium, silicon. And at the very, very core of the sun, we have iron. Now this, my friends, is the end of stars. When iron iron is the death of a star. Iron is what destroys stars. Because the amount of energy needed to fuse 2 iron atoms together is more than the sun has, or the star has. So once iron is produced and everything else is exhausted and the sun gets colder, it dies. That's when it starts to die. So up to iron, stars begin to die. So what happens? How does a star like that die? Well, what happens is gravity takes over, right? All the radiation's gone. So gravity takes over now, and it collapses. The star collapses. But the collapse is such an energetic event that it explodes outwards into space, and all that gas and all those elements, right? Think of all that gas enriched by all those elements. All that silicon and iron and carbon, it expels out into space in a supernova. And all that gas and dust goes out into space and becomes a nebula. And that's what becomes our sun again, right? Recycled stuff. And that becomes, like I said before, the protoplanetary disk, another star, and then us. But that's how a star explodes. Now, in this process, it happens to be that there's even more energy in the process of the explosion that all the other heavier elements that we're talking about before. So let's go back to the periodic table. Like I said, if you took notes, what I was saying was things up to iron, which is Fe, right? They cannot be produced in typical stars, but when they go supernova, all the other elements are produced in certain amounts. So in the supernova itself, there's enough energy for those elements to, all these rest of these elements to be produced, including uranium. So, again, that's why all the elements we see on the Earth are about mostly iron down, right? Maybe nickel, copper down. The other heavier elements are way more or less common, right? They're way more rare because supernovae are more rare. And the amount of time and amount of stuff produced in a supernova is way less than what is produced in the general life cycle of a star. So that's how that works. And what's left of that star is typically a white dwarf or typically a black hole even, right? There's enough mass there left from the core of that star to turn into a black hole. And here's a very interesting supernova animation. It's amazing stuff. This is an animation, of course, but this is what it would look like potentially if you were next to it. Think about that. That's amazing to understand, right? That's amazing to be able to know. One of the biggest explosions in space. And all that gas around it is superheated plasma, rich of elements. And over time, those elements become, again, another star system like ours. That's how we... So when we say we're made of star stuff, that's what we mean. That's what we mean. We're made of stuff produced in stars, in the cores of stars, billions of years ago. That many tabs is a crime? Oh no, I got 32 gigs of RAM, my friend. But anyway, yeah, that's how that works. Now, the Big Bang. So a lot of you guys had questions about the Big Bang. The Big Bang is a very highly misunderstood thing. It's also not very well understood. All the Big Bang means is the universe was smaller in its past, and then it expanded into a more colder, larger universe that we know today. So here's a great picture. Here's a fantastic picture. Okay. If we go far back enough, again, this is not a perfect analogy of we can't fathom the Big Bang. Our brains we can't fathom it. It's not. This is the best we can do. Right? This is a 2D image of a 4-dimensional event, right? So it's hard to describe the Big Bang, but essentially the Big Bang, come on. Okay. This is so annoying, guys. I'm sorry. Jesus. Okay. The Big Bang is the end of all of our knowledge about what the universe is. This is the entire universe, right? Think of the Big Bang as happening everywhere in the universe. The Big Bang happened where you're standing. The Big Bang happened everywhere in the universe. Everywhere. Even where you're standing. Okay? So think of this as the entire universe. Now, this is today's universe. Very, very large, right? Very big, very cold, spread out galaxies, right? If you look at these galaxies here, you notice that they're more spread out than everything here, right? So if we go back enough through time, right? This is 13.8 billion years ago, okay? The universe, as far as we can see, is about 14 billion years old. But if we go far back enough, we find that the universe was smaller, more dense. In other words, the stuff was more tightly packed together in the past. The universe was hotter because of this. The universe was way hotter. In fact, so hot that it's like 10 to the 25th degrees. It is so hot we can't even imagine how it was. But again, this is where our mathematics stops. This is where our physics just doesn't work anymore. Okay? This is as far back as we can see right here. But the point is that the universe today is large and cold, but it was smaller and hotter in the past. So how did it get to this moment? Well, it had to have expanded, right? So all of that space and time expanded into the universe today. That hot gas, right? All that matter was there at the Big Bang. All the matter in the universe today was at the Big Bang. It still existed. It was just a different state. It was just in it's called a quark-gluon plasma, a very different state than we're used to. It's not even a plasma. It's even more energetic than a plasma. Very, very, very hot stuff. And after the universe expanded very rapidly, it was able to condense into lighter material, or more, things like gases and stars, things like that. So the first stars appeared about 400 million years ago. Now, this green picture here, this is the CMB radiation. This is light from the Big Bang. This is light from the Big Bang. Right? When we look at telescopes, we can see back into the past, about 13 billion years ago, and we see this. We can see the light from the rapid expansion. Because the further back you see with telescopes, the further back in time you see. Because again, light takes time to travel to our eyes. So when you're looking through a telescope, that telescope is able to see photons that have traveled throughout the universe to get to our eyes today. So when we look at telescopes, we're looking at the past. And the further back you go, the further back you can see into the past. And what we see, the earliest image of the entire universe was this green image, where everything was very hot and densely packed together. But over time, it expanded and became the universe we know today, with galaxies and stars that are able to condense together and become our modern day universe. Now, how does this universe expand, right? What is causing the expansion? Well, we think that embedded in space and time, embedded within space and time is this energy called dark energy. And what happens is, it's kind of like gravity, but the reverse. Gravity loves to attract things together, right? If I throw a ball in the air, it tends to come down. So there's an attractive force happening there. But dark energy is a repulsive type of gravity that wants to repel things from one another. So imagine gravity, but in the reverse. And that's what we think exists within space and time, and it is causing the expansion of the universe. Because this energy infiltrates all the space and time, and because of this, it wants to repel things from another. It wants to repel space. It wants to rip it apart. So when you think of the Big Bang, think of a stretching, a ripping apart of space and time, right? It stretches apart like a rubber band, right? You're stretching it apart. That's how the Big Bang works. Now, it is very hard to fathom, okay? This is not a perfect picture or animation, but this is very analogous to what it would be like. This is how we think the universe is expanding. If you notice, all of the galaxies are expanding away from each other, right? All the galaxies are everything is moving away from each other. Every point of the universe is expanding away from the next. There is no center of the universe. So this picture is not even exactly correct. But the point is that every point of the universe is expanding away from each other. So if you imagine the expansion, it's happening everywhere, even where you're standing. Well, of course, gravity and the forces of nature allow us to be more compact or, tightly together. But between the galaxies, right? The space between the galaxies is expanding. That's what's expanding. It's the space and time between the galaxies. All of that, all of it, all of it, all of it. It's all expanding. And just like when you throw a ball in the air and it comes down with an accelerating force, right? When I throw a ball in the air, it comes down faster and faster, right? This is basic physics. We throw a ball in the air, it reaches a point where it stops. And the velocity is zero. And eventually it slowly comes back down again. Well, and then when it reaches the ground, it's at its fastest. The same with the expansion of the universe. Things further away from us are faster than things closer to us. So the universe is expanding. The universe, the other side of the universe, is expanding faster away than the closer parts of the universe to us. So that's how dark energy works. It's how strange it is. It's like gravity, but reverse of it. So hopefully that gave you a good picture of it. So when you think of the Big Bang, don't think of an explosion. Not at all. It's a different type of expansion. Think of it like a stretching of space-time. Even that's not correct totally, but the point is, generally speaking, it's a stretching of space and time itself. So that's how it happened. That's how the Big Bang happened. What caused it? What caused the initiation? That's still up for grabs. We still don't know what initiated the expansion, if there anything did. But what we think is there was a quantum field that fluctuated. If you have a strong enough fluctuation, you have an inflationary event happen. That's a basic idea of it. But again, this is up for grabs. We don't know. And no, you don't know either. Nobody knows how the Big Bang happened. Nobody. Not even your Bible. Not even your Quran. Nobody knows. Perhaps the answer is more difficult than what we even can imagine. We'll never know. Well, we may never know. But we might. We might know one day. So, yeah, that's how the Big Bang happened. Do you think there's other Big Bangs? Oh, that's actually a good idea. Let me go over the different models of the universe. There are many models of a potential multiverse or universe. The Big Bang's in Quran. Nope, it's not in the Quran. There is no science in the Quran. At all. There's no science at all. I'm trying to find the different models of the universe here, but I can't find a good picture of them. But yeah, here's one of the ideas that that beyond our Big Bang is another Big Bang. Beyond our Big Bang is another universe that goes in reverse. No, it's not fantasy. The multiverse is very possible. Very possible. A multiverse is very possible. It's just another universe. It's not that difficult to fathom. So we can imagine a Big Bang, and on the other side of it is another Big Bang, another universe that goes in the reverse, entropy. So in our universe, entropy increases. right? Disorder increases over time. But perhaps in the other universe, entropy goes the opposite way. We don't know. We don't know the full picture of the universe. Again, the Big Bang is the end of what we can know, what we see. We don't know anything beyond that. It's also possible that after a Big Bang, another Big Bang happens over and over again in a cyclic manner, right? You have universe after universe, right? Big Bang, collapses again, Big Bang, collapse again, Big Bang. That's another possibility. Again, these are just ideas. These are very speculative ideas. Nobody knows for sure. The universe is mysterious. The universe is a very big mystery. We don't know all the answers. As much as we want to know the answers, we don't have the answers. You know? This is why we made up religions, to make us feel better about the mystery. Religion was a way for us to feel better about ourselves in this mysterious place. So, yeah, what else did I want to show you today? Black holes are interesting things. Here's a very interesting simulation of a black hole eating up a star. So we know that black holes are very interesting things because they're not really objects. Black holes are actually like properties of space and time itself. An area of space-time that is so massive, that is so they're so dense that nothing can escape it. Not even light. Light can't escape a black hole because the gravity is so strong that it pulls in everything, including light itself. So here's a star that is being eaten by a black hole. Look at the sun. Imagine that's our sun, right? And there's a black hole right next to it, right? A black hole spins just like everything else. And in this spinning, right, it captures all that gas at the accretion disk, right? But after that point there, everything gets sucked in. So you also have jets streaming outwards because of the amount of magnetism that is being produced by the motion of a black hole. Very, very strange phenomenon. But look at the accretion disk form as a star gets eaten away. Gas is repelled, and then you also have gas going inside being sucked into the black hole itself. And the black hole becomes larger. Very, very amazing stuff. Very amazing stuff. CGI, yeah, of course it's CGI. But this is a real phenomenon that mathematically happens. It's not just imaginary. This is a real thing that happens. We can observe black holes. We know black holes exist. In fact, here's a real picture of a black hole. Here's a real picture that we've taken of a black hole. The first one. This was taken in 2019. And you can see the accretion disk. Right? This is superheated gas that surrounds the black hole. There is the black hole itself. It's black because light doesn't come out of it. But around it, we can see that the gas around it that is superheated by the black hole itself because of its motion. But that's amazing to understand. Can a black hole be inside another black hole? Yeah, black holes can merge together. Let me see if I can find black hole merge. Yeah, so here's a great picture. Here's a great animation of two black holes. What happens is they like to orbit around each other. They circle around each other. They kind of do this dance. Gravitational dance. And again, this is slow motion, but once they get close enough, they spin very, very quickly. Streams of gas start to connect the disks, right? So it becomes one disk. Magnetic and gravitational forces heat up the gas. Right? A lot of energy there, heating up the gas. It produces radiation and X-rays. Again, X-rays are just light. UV is just light. It's all light. Okay, now they're merging together. Look at that. Space and time becomes distorted. Inside of the black hole, weird stuff happens. In fact, we don't even know what happens inside of it. But whenever you get near a black hole, time slows down. In fact, inside of a black hole, time stops. The ticking of time stops inside of a black hole. Gravity can affect time. Speed can affect time. Or at least your perception of time. Right? How you perceive time relative to some other area of the universe can change depending on how much gravity you experience, how much mass you have, how much velocity you have. In fact, the faster you move through space, the slower time moves for you. Galaxies can also collide. Here's a galaxy. Here's the Milky Way galaxy. They eventually will collide. Another dance, another gravitational dance. Look at this. Their stars are... Remember, all these are stars. They're colliding. Black holes are in the center of the galaxy, and now they merge together to make one big black hole, one big galaxy. And again, this takes millions of years to happen. We're talking hundreds of millions of years, right? We're talking like 300 million years for this to happen, fully merge together. But this is how we will one day merge with Andromeda. This is us. This is literally our galaxy. We're on a collision course with Andromeda. This is how we will end up in about 3 billion years from now. Eventually, we will see us merge with another galaxy to become a bigger galaxy. It's going to happen. Another one of my favorite videos is the scale of the universe. I want to show you guys the scale. But before I do this, I'll answer some questions. It's going to happen? Yes, it's going to happen. We know because we can measure galaxies and how fast they're moving. We can see galaxies moving. When we look out in space, we can see the movement of galaxies based on the light that they send out to us. We can see that as light moves across space, it stretches with space. So, because of the wavelength of light, and this is amazing. We have to take a look at the light spectrum for this because this is very, very counterintuitive if you don't have a proper animation. Here. All right, let's see if you can see this. This. Perfect. Come on. I hate this glare stuff. Alright, let's see if I can do this. Perfect. Okay. So, here we have the spectrum of light. Again, this is not all the light, all the colors you see in the rainbow. Those are not all the possible spectrums of light. Those aren't all the possible colors, right? That's just what we can see with our eyes. But look at how small this is. Look at this. All these spectrums, all these wavelengths come together and they form this tiny sliver of the total light spectrum that there is. So here, for example, is visible light. In this spectrum here, these wavelengths are about, a couple hundred nanometers, 500 nanometers, right? Very small, atom-sized wavelengths. Now, when we go to infrared, they're longer. I'm sorry, let's go to ultraviolet. Ultraviolet is more intense radiation, hence it's going to be shorter wavelength, right? The shorter the wavelength, the more energy there is, right? Because think of how short the wavelength is. But the speed is the same, which means they're going to be stronger, more energy in that wave. X-rays are even shorter, even more energy. And gamma rays are some of the strongest light waves there are. Super strong waves. Because they're very, very short wavelengths. And that's what makes them so strong. Now, when it comes to infrared, they're longer. So, because of how long they are, there's less energy there in the wave. Radio waves, some of these waves are centimeters or even meters across. Right? The radio waves that are being sent out through your house and Wi-Fi and through the satellites, they're radio waves. They're meters long. Meters long, right? They're very big waves, less energy. But this is how light works. Light is a wave. And depending on the wavelength, that it tells you the intensity of the light, right? So now that we have this, we can understand that as light from a galaxy moves across space, space stretches. And because of this, that light that travels with space and time also stretches with space-time. So that light becomes a longer wavelength. Right? So now that gamma ray that was emitted from a galaxy a million light years away is now, because of the stretching of that wave, now it's an infrared wave or a visible wave. And that's what we see with telescopes. We can see the light in those infrared and visible and UV light from stuff billions of years ago. We also can see galaxies moving through space because their light is being stretched through space. Right? We can take a look at the redshifting of the galaxies. That's why they're red. That's called redshift, because redder light tends to be longer than blue. Blue light tends to be shorter. Right? So the red light that is emitted from galaxies means that they're moving away from us because they're getting longer. They're stretching away from us. Whereas something getting closer to us is the light is being compressed. Hence, they're shorter wavelengths. Right? So when something's coming close to us in terms of their light, we know because the light is compressed blue. Whereas light that is, galaxies that are moving away from us, they're redder. Hence, redshifted. So that's how we know the Big Bang happens. Because when we take a look at all the galaxies in the universe, we can see the redshifting of all the galaxies. And that means that they're all moving away from us, all expanding away from us. Only a few of them are blue shifted. Andromeda and a few more. But the rest of them are all red shifted, which means that they're moving away from us. And in fact, there's a point in space where we can't see any further because light because the expansion of the universe is expanding faster than light itself. The universe is expanding in some regions faster than light itself, which means the light that comes to us from those galaxies can no longer reach us. Which means there is a point in the universe that we'll never be able to see, ever. That's pretty scary. That there are stuff out there that we'll never see. Anyway, what was I gonna say? Yeah, this is amazing stuff, guys. This is mind-boggling stuff to understand and to learn. Not just life, but space, black holes, and there's so much to learn. There's so many things to understand about the world that how can you possibly be bored? How can you be bored by this? How can you be bored by life and space and Earth and life? There's nothing to be bored about. There's so much to learn and understand. And here's a great example of that. Let's take a look at the scale of the universe. Let's take a look at how big this stuff is. This place is. All right, here's California. Here's America. There's our planet. That's our planet. From far away, right? That's it. That's all we got. This one little blue dot. One little blue world. Now, look at it. It becomes a little dot. You can barely see it the further away you go. There's the moon. There's some asteroids. We're surrounded by asteroids. There's Mars, Venus, Mercury, the sun. The sun, far enough away, becomes another star. Right? There's an entire solar system. The sun, far enough away, becomes just another star. That's it. We're just another star compared to all the other stars out there. Okay, now we're 100 light years away. A light year is how much time it takes for light to travel. A light year is the distance it takes light to travel in 1 year, Earth year. Now here's our galaxy. Let's go back to that. So here we are, and look, here's our galaxy. We're on the outer edge of a galaxy. We're not the center of it. We're not even the center of the galaxy. We're not even the center of the galaxy. We're on the outskirts of a galaxy, somewhere out there in the countryside. Now the galaxy's a dot. The further out we go. Now there's lots of galaxies. Now there's networks of galaxies. Look at this. Clusters of galaxies. Each one of these dots is billions of stars. A whole entire galaxy. Look at this. That's how many galaxies there are in the universe. Trillions of galaxies. Look at this. That's how big the universe is. That's how much stuff there is. That's how many galaxies there are. Each one of these pixels is a galaxy. Full of billions of stars each. Billions of suns. Billions of planets. Each dot here. Look how big the universe is. Look how much stuff there is. Does it look like we're the center? Does it look like that we're the main characters of the show here? No, we're not even a pixel of a pixel. We're not even a fraction of a dot. But let's zoom back in. Back to our galaxy. Back to our star system. The outer Oort cloud full of gas and dust and ice. Here's the Earth. Look at this special planet, the Earth. It's blue. And there's a person. But hold on, let's see what's inside. Okay, we got the eye, got the pupil, the iris. Oh, we got blood vessels here, right? Inside of your blood vessels are blood cells that distribute the oxygen throughout your body that make you alive, right? That's what makes you alive here. All that stuff that happens inside of your blood. In your vessels. There's a cell. There's an individual cell. Oh, look inside here. Now we see chromosomes. Look at this. Chromosomes. These are strands of DNA molecules. Strands of DNA molecules inside of your cell. Now, here's an individual DNA molecule. Take a look at this. Your DNA is made of molecules, right? There's even a finer structure of your DNA. Polymers. These are long chains of, simple molecules. And combined together, they make your DNA. Each one of these are now atoms, right? Carbon atoms. Here's an oxygen atom. Take a look at the nucleus inside. There's a couple electrons there. Electrons are orbiting around the nucleus. A lot of empty space inside. There's neutrons and protons, and inside of the protons and neutrons are quarks, the smallest things we can measure, the smallest pieces of matter, particles that we can possibly measure. That's as far back as we can see. That's how small we can go. But inside of you, look at this, is an entire universe of stuff. Not only is there a universe out there, there's also a universe in here, inside of you. Another world inside of you. Even more stuff to fathom, even more things to understand and contemplate inside of our bodies. There's another universe. You're made of a universe. But look at how that... If you aren't mind blown by this, I don't know what will make you mind blown. Because our brains can barely understand this. Our brains can barely understand these scales. We're not used to it. What blows your mind is that the oceans are full of salt. Well, the Earth's crust is full of salts. You feel so entitled. Well, hey, we're here. We're alive. Think of what we are. Think of what we are. We're conscious. We're aware of this. We're able to understand the world. That's amazing. We're able to understand this. That's amazing. What are the chances that we're here, able to do this, understand the world around us? And not just that, but also understand the mystery of it. The mystery is even more exciting and thrilling to understand, to fathom, that there's mystery out there, there's things we don't even understand. That's amazing. You guys keep saying God, but think of why you're saying that. You're saying that because you don't want to accept the fact that there's mystery. You just want to have the answers. Oh, yeah, trust me, it's all God, it's all God. How do you know that? What is God made of? What does God do? Who made God? How did God get there? You're not answering anything by saying God did it. You're just opening up a new can of worms. Well, how did God get there? All these questions you can't answer. Maybe they're unanswerable questions. Maybe we will never know the answer. You can't answer questions either. Yeah, the difference is I admit it. I admit I don't have all the answers. I humbly admit I don't have all the answers. I don't claim to know that there's a God. I don't claim to know that. But you do. Look who is claiming to know everything. You. You're the one claiming to know everything. That God did it. Trust me, God did it. Not me. I'm looking at the mystery going, yeah, this is mysterious. We don't have all the answers. We don't have all the answers, right? And I graciously accept that. It makes me happy to know that there are things out there waiting to be discovered, that we don't have all the answers. That's thrilling to understand. That's amazing to contemplate. Here's one of the greatest pictures ever taken by mankind. This is a real photo of the Earth. Do you guys see it? Do you guys see the Earth? Do you guys see the Earth? Oh, it's right there. It's that one pixel. It's that one little dot. It's right there, if you can barely see it, right? This is a picture of the Earth taken 4 billion miles away, right? It's just a dot. That's all it is. We're just a dot. That's it. Just a dot, right? On that dot, everything you ever known, every person you've ever seen, every person, every animal, everything you've ever seen, everything you've ever known on that one dot, right? That's a perspective that you can't get without science. Look how fragile that looked, right? Look how fragile we are. We're barely hanging on. We're barely here. We're this one planet. All we got's each other. All we got is our friends and family and our understanding of things. And learning is amazing. Learning is great. That's what makes me hopeful. Every scientific discovery we make, every time we learn more about each other, every time we learn more about the universe, it makes me hopeful. It makes me proud to be human. Because we're still learning. We're always learning, and we can do better. There's a lot of potential out there. We can do amazing things. Look what we can do. We can go to Mars. We can land on the moon. We can develop technologies. We can make super colliders and particle accelerators. Right? We can do amazing things. So that's why I have hope for us. That's why I continue to fight for science. And right, because it's all we got. I look back on that one dot and I say, wow, let's not mess it up. Let's not destroy it. Let's not fuck this up, right? Let's do something good. Let's change the world. Let's make it better. Let's make use of our lives. All we have is faith a dark matter exists. What blows my mind, how do you think God is real? Dark matter is a observable phenomenon. Dark matter is something we observe with telescopes, gravitational lensing. I have a video of this on I did another Science Live where I talk about dark matter, and you can go look that up too on my YouTube. If you guys want more of this, go to my YouTube. I have lots of more lives, science stuff. Link in bio. But dark matter is something we observe. We can see the gravitational effects of dark matter. We can see it. That's how we know it's there. We can see the changes of... We can see the light. We can see the light bending around dark matter. We can see light bending around dark matter. So we know it's there. We just don't know exactly what it is. But we will know eventually. Again, what's better? To sit there and go, trust me, God did it. Or maybe there's something more than God. Maybe there's something more intriguing and extravagant and amazing than God. This is why I think religion is a very limiting thing. Religion is a very limiting concept to me. I think that there's much more out there to be amazed about. Look at all the things we just learned today. Right? Look at how many things there are to learn. And by the way, everything you guys just learned today, our ancestors had no idea about. Think about that. For millions of years, our ancestors looked up at the moon and said, "What is that?" They didn't know what the moon was. They looked at the stars and said, "What's that?" Now we know. Now we know what the stars are. For the first time in human history, we know what the stars are. We know how far away they are. This is amazing. This is an amazing time to be alive, where we know more than any person that ever existed. You know more today than Isaac Newton. Think about that. You guys say that Newton was the smartest man. Well, you know more than him. We have more knowledge today than every person in the past. That's amazing. And the fact that we're able to understand this and learn even more makes life amazing to me. It gives me hope and happiness. It makes me excited to be alive. Science and evolution is what you are making your God. No, I don't believe in something like that. See, I don't attach myself to beliefs. Wherever the evidence leads, I'll follow. But I don't build a puzzle and pretend I know the answer before I build it. I wait. I build, I speculate, I observe, I gather evidence. Oh, what can this piece be? Okay, this could be this. I don't just say, oh, it must be this. It must be a cat. I keep building the puzzle until I get the full answer. But maybe we'll never get the full answer. And that's okay. That's okay. But we're still building the puzzle. See, what you want to do is you want to say, God did it. Trust me. God did it. As if you have the answer to the puzzle. We haven't even built the puzzle yet. We've barely just begun building the puzzle. We have 2 pieces. And you're already saying God did it. No, let's build more. Let's learn more. Let's discover more about it before we say God. By the way, you don't even know what God is. It's just a word. God is a word. You guys are saying God as if we know what that means. You don't even know what it means. Nobody does. It's a word, and it means nothing.